Ladies and gentlemen, my name is Josh Hosteller. I'm part of Group 6, which is the Smart Driveway Group. This is just a brief overview of what I'm going to be talking about today. Just a brief introduction of who's part of this group. We have Dr. Miller, who's our advisor, Dr. Ridenauer, who is our coordinator, Kali Trumi, who's a civil engineer and the team leader. He's the fluid flow analyst. We have Wani, who's a mechanical engineer, the secretary, and the HVAC analyst and document manager. Mohammed Bajabab, who's a mechanical engineer, the treasurer, and the CAD designer and heat transfer analyst. And I'm Josh Hosteller. I'm a civil engineer, the lead designer, and the thermodynamic cycle analyst. This is our abstract, which I'll touch on in the next slide. One of the main challenges that we've found with people who have residential driveways is the accumulation and formation of ice and snow on the driveway. This normally leads to reduced traction in tires and with people walking on the driveway, and accidents happen and people can fall and injure themselves. So we decided that a heated driveway was the best solution for this problem. So we came up with a few candidate solutions, the first of which was a solar powered heated driveway system. The problem that we found with this was the implementation of the project is very costly, and when the solar panels aren't in direct sunlight, they don't have a very high efficiency, obviously. The next solution that we came up with was a chemical deicer operation. The problem that we found with this was that this solution still required manual removal of the snow, even though there was supposed to be a solution for that, and also it required you to spray chemicals, which isn't environmentally friendly. So the solution that we came up with was to integrate a system of pipes underneath of the driveway. It would circulate a mixture of antifreeze solution, which we came up with, where you're using propylene glycol and water. And it just circulates that around underneath the driveway. It's energy efficient, it's durable, it's cost effective, environmentally sound, and it operates only when necessary. So this solution, this project seeks to explore the most applicable heated driveway alternative system and installation techniques. It eliminates salt damage to the concrete, it eliminates mechanical damage to the property, it eliminates piled snow and the use of chemicals, and it reduces the potential for back problems and cardiac problems from shoveling the snow. This is a project overview. So the whole system starts when you turn the power on. That's the main power for the whole system. And then you have the thermostat, which controls the temperature for the boiler, which is what heats up the fluid and sends it out throughout the system. And we also have a deadband thermostat in our system. This thermostat turns the whole system on when it gets to 31 degrees Fahrenheit and turns the whole system off when it gets to 35 degrees Fahrenheit. The reason we decided to put this into our system was so that you don't have to worry about turning the system on and off yourself. So if you're sleeping and overnight it snows, it'll turn on because it has to be below freezing for that snow to stick. And then it'll melt the snow, so you don't have to worry about waking up early to shovel yourself out of your driveway, or if you're at work, you don't have to worry about coming home and dealing with snow or ice on your driveway. This is another kind of overview with a more detailed idea of what we're going to be putting underneath the driveway system. So you're going to have the boiler here pumping out the heated propylene glycol and water solution out into the system, and it's going to circulate around. And then it's going to, once it gets to the center, it's going to return back. And the reason we decided to go with that layout for the pipes underneath the system is because it's the best way to evenly distribute the heated solution throughout the driveway. It doesn't really miss any spots, which was a problem that we found with some of the other pipe layouts from the system. This is just kind of like a subsurface layout. If you were kind of looking at it from like face on. On the bottom, you're going to have a layer, on the bottom and sides, you're going to have a layer of insulation, and then on top of that, you're going to have wire mesh, and then the piping is going to be laid on top of that, And then on top of everything, you're going to have the concrete, which would be the driveway surface. For our technical design constraints, we had a heat source output, and for that, in Philadelphia, a Class 1 required heat output of 97 BTUs per feet squared, with 10° Fahrenheit air temperature is required. Our surface materials are going to be a concrete slab of 4 inches to 6 inches. This is the optimal thickness to ensure the best performance of melting snow. The efficiency, the heating system will effectively melt the snow at 1 inch per hour. The insulation is going to be a 2-inch high-density foam board, which will act as an under slab and side insulation for the driveway perimeter. And the heating fluid is going to be 50% propylene glycol and 50% water mixture, and this cannot exceed 150 degrees Fahrenheit to keep, just so this won't damage the concrete or the system itself. For the non-technical design constraints, we had an economic constraint. We expect the cost of the system to be less than $1,000. For the safety, we're going to be following the Radiant Panel Association guidelines. For the manufacturability, the size of the driveway will be 12 feet by 20 feet, and we just chose these numbers arbitrarily. This driveway system can be redesigned for any width or length. It's going to be environmentally friendly. The system will be using non-toxic heating fluid mixture, and for sustainability, it will be a low-maintenance system. The major design challenges that we came up with while we were designing it were to develop a heating system that would require the least amount of output, or the least amount of maintenance throughout its lifespan, complete the sealing of the heating system underneath the driveway, and keep the cost of the energy consumption to a minimum, and then to find a way to test the heated driveway system. This is just our estimated cost. So our boiler we estimate to be anywhere from $300 to $400. The PEX tubing, which is going to be the tubing that we lay out underneath the driveway, would be anywhere from $100 to $150. The pump we found to be anywhere from $50 to $100. The brass fittings and pressure gauges would be anywhere from $50 to $100. And other miscellaneous expenditures that we may need would be around $200, we figure, which would total out to be less than $1,000. So for our approach, we designed, we found an industry-used manual that other companies use when they're designing their heated driveway system. It's based on the ASHRAE handbook, which is what's used. It's got a bunch of guidelines and things for systems such as this one. So the first thing we had to do was determine an outdoor temperature. For this, we decided to use 10 degrees Fahrenheit. Wind speed, we used 10 miles per hour. Surface temperature of 35 degrees Fahrenheit and a differential temperature of 25 degrees Fahrenheit. And the differential temperature is just the temperature at which the fluid is supplied to the system as opposed to when it returns to the boiler. And these values that we determined gave us heat flux of 95 BTUs per hour per feet squared, a supply fluid temperature of 126 degrees Fahrenheit, and a 12-inch off-center tubing distance. The total area for the system we said would be 12 feet by 20 feet, which gave 240-foot squared area. And then to calculate the total BTUs per hour, we multiplied that by the heat flux, which gave 22,800 BTUs per hour, which is the minimum output that our boiler would need, which is the minimum BTUs per hour that our boiler would need to put out. And then for the total piping under the slab, we calculated that to be 201 feet. And then for the total amount of tubing, we calculated that to be 241 feet. And we calculated this by pretty much just laying out our driveway system and drawing the piping underneath the system. And we calculated that to be 201 feet. And the reason we got 241 feet for the total tubing was because we needed 20 feet to get from the boiler to the system, and another 20 feet to get from the system back to the boiler. So then from the book, which we didn't realize at the time, but this is kind of what we had just done previously. The book had us calculate an active loop length of 200 feet, which was only a foot off from the distance from the total length of tubing that we had calculated, which was 201 feet. This gave us a number of loops to be one loop and a total leader length of 20 feet, which we didn't realize at the time, but which should have been multiplied by 2 because it was 20 feet going in and then 20 feet coming back out. So the book would have given us a total loop length of 240 feet. Like we said, we used a 50% glycol solution, and the reason we used 50% was because the way it mixes with the water, it gives a better temperature for us to use. And then for the flow per foot tubing, we calculated that to be 0.0082 gallons per minute. The flow per loop would be 1.64 gallons per minute, and the total system flow would again be 1.64 gallons per minute. And then the head pressure drop per foot would be 0.04767 drop per feet, and the head pressure drop per loop would be 10.5 foot per head. And then this is just more of kind of a detailed picture of what we had, like the subsurface layout of what we had. So you can see here that you have the ground, and then on top of that would be the insulation, and then the wire mesh with the tubing tied down to the wire mesh, the insulation on the side so that you didn't lose it, so you don't lose any heat out the side, and then you have the concrete laid out on top. And then for summary, so for Senior Design 1, we finalized our design layout. We got more familiar with each part of the system, and we completed the required calculations, or most of the required calculations, and we came up with a full budget analysis. So over the summer and for Senior Design 2, we plan on running a simulation to see the efficiency of the system, to keep the total cost of our system under $1,000, and to build a functioning prototype of the system. Thank you for your attention.
Any questions?
Calculations? Which,
The temperature?
the temperature?
Yeah.
Okay, this one?
Yeah.
All right.
You have all those temperatures 10 degrees Fahrenheit and the surface temperature 35 degrees. What
Yeah.
is your water glycol temperature?
The temperature of the fluid inside of there was going to be 126 degrees Fahrenheit coming into the system,
Okay.
and then with the differential it'd be 101 coming back. So
How did you come up with 35 degrees and given 126 degrees Fahrenheit?
how do we come up with the 35?
Yes.
We just picked that number arbitrarily. So because the snow and because the freezing temperature is 32 degrees Fahrenheit, we obviously had to choose something above 32 to get it to melt, and we chose 35. The book, the manual that we used said they used 34, but we decided to use 35 to give it just a little bit extra just in case. But we just kind of picked that number. It wasn't a calculated number.
Well, anyway, when you have a given temperature 126 degrees Fahrenheit, fluid temperature, right?
Right.
And you said you have 4 to 6 inch slab.
Mm-hmm.
And what is the RT?
What's the what? I'm sorry.
Temperature drop through the slab.
To be honest, I'm not really sure. The manual that we used, well, because the manual that we used was based on the ASHRAE handbook, and in the ASHRAE handbook, it uses a lot of advanced thermodynamic equations that we're not really.
You need to take a look at that.
Okay.
Another thing is that your surface temperature to deal with 1, fluid temperature, 2, your flow rate. You haven't talked about what's the pumping, velocity, what's the
Right.
flow rate, right? If your flow rate is low, it's different.
Oh, yeah,
High is
okay.
Cold, you may end up with temperature much lower than what you want.
Okay.
Or may end up much higher.
Right.
So
We'll take a look.
surface temperature is all to do with your control. You don't have equation, so you very likely you know to get away.
Okay.
Second is why you want to use pump fluid, not using resistive, wire, because I have seen most of the heated driveways, they just use the heating wires.
Right.
The electrical wires, it's
Yeah.
much easier than pump loop. What's the reason?
Can you repeat? I'm sorry. You're in the back of the room. It's hard. It's a little bit harder to hear you, but
Typically, driveways, they go to the heating driveways.
yeah.
They always use electrical heat wires.
Oh, okay.
Why do you use pump loop?
The reason we used this was because it was when we designed it out, we were weighing out the pros and cons of the electrical and the fluid systems. And with the electrical, we kind of found that sometimes like it would require a little bit more maintenance in case something went wrong with the wiring underneath the driveway. You would have to rip up the whole driveway or something like that. And it just made, I guess, more sense for us to go this route. I had seen one of these driveways done before using, I think he used ethylene glycol instead of propylene glycol, which the difference there is just, the ethylene glycol is a better solution to use, but we went propylene because it's more environmentally friendly. In case it leaks out, you don't have to worry about having to call like a hazardous materials team. But when we were designing it, we decided to go this route. It seemed more, I guess, better for.
Now, the main reason I asked you this question,
Yeah.
where do you keep your hot water tank?
The hot water, the boiler.
Yeah, the boiler.
You can keep that in the. It depends on how far away you want it from your house. The way we designed it, just arbitrarily for this one, we just chose like 20 feet away. But you can keep it in your driveway, in your garage if you have a garage close to your driveway. Or if not, you can put it in your basement, which would require a little bit more calculations because you would have to overcome for it to come up out of the basement and into the system. But you can keep it.
Do you know how much loss it would be?
If
Depends on where you put your boiler.
right,
You're running the hot water through underground, right?
yeah,
Or somewhere. You have to have good insulation around to reduce the thermal losses.
for the. I'm sorry.
For the piping,
Yeah.
because you have to have piping from your boiler
Oh.
to your heating system.
Right. Yeah.
And you have extra losses right over there.
Yeah, that's
How
true.
much losses?
We hadn't calculated for that in this, but take that under advisement.
So in other words, is that depends on where you put, you may end up and you will find out that your loss is too high.
Right.
Didn't get it anything.
Yeah.
So, do you-
It depends on where you put it. For our purposes, we just designed it kind of as if it was just right there. Didn't need anything else, but
It will be part of the calculations.
yeah.
If you want to find out all system efficiency.
Okay.
Why this is bad, that's, you have
All right.
Any questions? We still have 2 minutes. Okay, I'll ask a question. Now, when you have your thermostat, what you call dead band
Mhm.
thermostat, but when the temperature goes to 31 degrees, it will turn on
Right.
the system. Now, does it check for the existence of snow or doesn't?
It won't, and the reason that we decided to do that was because if it was just checking for the moisture, like we weren't really sure how to exactly, because it's 2 civil engineers, 2 mechanical engineers. We don't have a lot of electrical help on this one, so we weren't exactly sure how to get like something that would detect moisture, and then in the air, and then you also, if it's just detecting the moisture and not temperature, then you have to, then if it's like above 32 degrees, then you have to worry about that. But we weren't exactly sure how to incorporate the
Yeah,
moisture
because
aspect.
this way you are going to waste energy. But anyway, there must be a sensor which can detect something. Now, the other thing is that the configuration for the tubing you have,
Yeah,
so it may be efficient from the energy point of view, but if something breaks down and the whole system goes down the drain.
right.
So if you use the radiator system,
Yeah.
that actually will be more efficient because you can actually have it across the driveway, and you can put some redundancy in it.
Yeah.
And if one tube, breaks or something, you can take the other one instead.
Okay.
So we should really have some allowances.
Yeah.
Because the current system was not meant to give the best energy consumption, but once a pipe breaks down, that's it.
Yeah.
Okay. Okay. Any more questions? Thank you.